Today's lesson is all about indefinite integrals. For the past couple of lessons, our focus has been on the definite integral, which, through the fundamental theorem of calculus, allowed us to very quickly find the area bounded by the curve, the x-axis, over some sort of closed interval. So if you take a look at our first objective, indefinite integrals, basically it's the same thing as antidifferentiation. Evaluate an indefinite integral by finding a general antiderivative. Okay, the second objective, to be quite honest with you, doesn't seem to flow with the first, but hey, that's just the way the book was constructed. We're going to use integrals of rate of change to find net change. So the second objective actually focuses back on those definite integrals. Here, let's go ahead and start with a warm-up question like we sometimes do, sometimes as in almost all the time. So the first part of it, evaluate the definite integral from 0 to 1. 3x squared plus 5 with respect to x. Okay, so assuming that you have the problem written down, the very first thing that you want to do is find the antiderivative. So we're going to increase the power by 1, divide by it, so that'd be 3x cubed over 3, which just reduces to x cubed, and then plus 5x. And then the fundamental theorem of calculus is really going to help us out here. We're going to evaluate that from 0 to 1, but we plug that 1 in first, and then we subtract plugging in the 0. Polynomial is very nice, especially when we have to plug in the 0, because it's going to be a whole bunch of nothing. So we're just going to essentially have 1 plus 5. We get 6, which of course is a number, and that number represents the area bounded by this curve. This thing is completely above the x-axis, so this is the area from 0 to 1 above the x-axis below that curve. Okay. Second part of this, find the antiderivative of f of x is equal to 3x squared plus 5. Wait a minute, didn't we just do that? Isn't the antiderivative just right there? It's just x cubed plus 5x, but don't forget your plus c, your constant of integration, and of course we get a function here, so big difference. A definite integral is going to give us a number, and an antiderivative is going to give us, well, it says a function, but really with that plus c, it's an infinite number of functions. All right, so notice that they do have something in common, right? Our first step in evaluating a definite integral is to first find the antiderivative. Okay, so since that is the case, we're going to adopt the exact same symbol for antidifferentiation, or if you prefer, indefinite integration. Means the same thing, but this symbol is going to be unadorned, which means that we're going to take these little limits of integration off, just as an operator that tells us to find the antiderivative. And then, of course, don't forget your little plus c at the end. Okay, so that brings us to our first objective, being able to evaluate indefinite integrals by finding an antiderivative, a general antiderivative. So remember from this pick, we've got a parabola. Its antiderivative would be this cubic equation, and the plus c is being represented by like all of these various red functions that are being translated up and down. Okay, so since we're using this symbol to represent finding an antiderivative, you're going to see that it's going to be much more elegant to write down instead of just, oh, just capitalize the letter, or, oh, just remove the little prime mark here. We're going to have the stretched out looking S thing. That's the integration symbol that's right there. And that's going to symbolize us taking the antiderivative of this f of x function, which is called the integrand. The dx, that's the differential with x. It just tells us the variable of integration. Anything else would be held as a constant. The capital F of x, of course, oh wait, I think it's plus c first. The plus c is our constant of integration. Remember, we have to add that because if you take the derivative of a constant, you lose it, and you don't know what it is without some sort of initial condition. Capital f of x, that's our antiderivative. If you were to take the derivative of that guy, of course, you get the integrand back. Okay, so again, the process of antidifferentiation is the same thing as indefinite integration, and we're going to symbolize it with just this unadorned integral sign. Okay, like I said, it's going to make it a lot more elegant for us to like write ourselves a little table of integrals. We're going to see that in just a minute. Let's compare and contrast definite versus indefinite integrals here. Okay, so definite versus indefinite. Whenever I solve a definite integral, what do I get? I just get a number, right? It could be positive, could be negative, could be zero, and that number is supposed to represent a net area bounded by that curve and the x-axis. Indefinite integral, whenever I solve it, I'm going to get a family of functions. Not just one function, but an infinite number because we're going to add that little plus c at the end. And it represents the general antiderivative of your function. And not only that, they're linked by the fact that in order to find the number over here on this definite integral, you must first find the antiderivative of your function. Okay, so this is what I was talking about, that with the little integration symbol, you can see that just like with all the differentiation rules, you can do the same kind of thing in a much more compact and easy to read fashion for a table of integrals. Okay, so I'm going to call your attention just a couple of them. Our power rule in particular. So when I take the derivative of x to the n, we play that leapfrog game. We multiply by the coefficient, and then we're going to subtract one from the exponent. Whenever I work backwards for indefinite integrals, I'm going to add one to the exponent and divide by that exponent. Notice that that exponent cannot be -1. If it is -1, hey, then you get a completely different function, and its antiderivative is the natural log of the absolute value of x. Don't forget your plus c. Why the absolute value? Well, remember that the domain of this original function only excludes 0, and it still includes all the negative numbers. However, its antiderivative as the natural log is only greater than 0. Hey, here's the graph of that thing, right? So we have to get rid of all of this stuff that's over there. Okay, the last thing that I'm going to call your attention to are all of the trig functions, just to recap there. That whenever I take the derivative of a cofunction, like this guy right here, I'm supposed to end up with a negative derivative. Okay, so it works backwards here for anti-differentiation. It's not if I start with a cofunction and its answer being negative. No, 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 no. It's if the answer itself is a cofunction. So you can see here when I take the antiderivative of sine, you get cosine. It's going to end up being negative because I ended with a cofunction. You can see that playing out right here with antiderivative cosecant squared is a negative cotangent. Antiderivative cosecant cotangent is negative cosecant plus c. Of course, if you ever forget, you could just take the derivative of your antiderivative and you should go back to the integrand.